My own personal belief is that the ideal lecture or summer school talk or something like the ideal lecture should, you lay out a few facts to begin with, and then you use logic and reason and insight to develop consequences of those in an increasingly interesting set of discoveries. And then by the end, you feel like every step in retrospect was practically inevitable in its logical beauty. And these lectures I will be giving are exactly the opposite of the ideal lecture from that criteria. I will lay out a few facts, make some observations, raise some questions, notice some puzzles, mention a few more facts, and then we'll be done. So it's all very, very informal, loosey-goosey, and feel free to chime in at any time. It's all, because I think it is appropriate for the state of the field where we are right now. We're talking about the early universe and cosmology and trying to relate it to the philosophical questions of past hypothesis and entropy and time asymmetry. And my confidence that we're almost there getting the final right answers has decreased with time over the last 10 years. So it's more about inspiring the younger generation to figure these things out than pushing my own theory. So a good starting point, I think, is just to imagine, think epistemologically, okay? Think about what we know and why we're okay to say that we know it. So imagine that we're in this room. Here we are in this room. And imagine, to make things simple, that the doors were closed and the window shades were down. So you can't see outside this room, okay? So there's an extreme skeptical point of view that says, I don't even know if this room exists and you exist. I could be in a computer simulation or the dream of a demon or something like that. So let's just assume that none of those things are valid words, that we can take for granted what's in this room, the macroscopic information. We obviously don't know everything in this room. We don't have access to the microstate. We don't know where every single atom is and what its velocity is. But we know certain macroscopic things, how many people there are, etc. And included in that macroscopic knowledge is the state of what we think we have in our brains. We think that we know something about what is outside this room. So there is an environment. You can imagine this as big as you like. We imagine that if you go outside the room, we believe there is something called UC Santa Cruz. There are deer, there are redwoods, there's the solar system and the galaxy and the universe, and so forth. Furthermore, we think we know some things about the history. We think we know some things about the past, right? Certain things happen. We've had 2 weeks of lectures that you've heard. We're pretty sure that Fred lectured this morning. We think we have some knowledge of the laws of physics and logic and math, and so forth. And so the questions are, what right do we have? What is the justification for believing that, granting everything that is in this room right now? So the first observation is that our knowledge about what is outside, the existence of the deer and the solar system and so forth, is really directly related to knowledge of the past, right? We think there are deer out there because we've been out there and we've seen the deer, and we don't think that they all disappeared. We have some knowledge of the laws of physics from our experience and other people's experience doing experiments, and we use that to say that it is probably not true that there was a bubble of true vacuum that nucleated moments ago and is speeding towards us at the speed of light and has destroyed all the deer, will destroy us any second now. I pause when I say that. If this were a movie, I'd be dead right now, right? So we know that even we could be in a computer simulation. We are not in a Hollywood movie because we can say things like that without facing the consequences. So it's really a statement about the past. How do we know things about the environment? Well, because we think we know things about the past. What right do we have to say that we know things about the past? And David Albert already talked a lot about this, but let me just sort of put it into my language. You might think that given our knowledge of what's going on here in this room simply determines to some approximation, to some degree of reliability, what is outside the room. You might think that the fact that I have a thought in my head, a remembrance of what the deer looked like yesterday when I saw it, means that it is very likely to be the case that the state of the world outside the room has deer in it. You might think that. By itself, I think that that's not at all true. And this is where the conundrums begin. In classical mechanics, if we think about, if we model the stuff going on inside the room and the stuff going outside as some set of particles that evolve through phase space, knowing the positions and the momenta of all the particles in here, including the fact that there are little images of deer inside our brains, tells us absolutely nothing at all about the positions and the momenta of the particles outside. You can construct any state you want with particles doing whatever you want out here, no matter what the particles are doing inside there. The two subsystems are independent. That's not 100% exactly true. If you had Newtonian gravity, then the gravitational potential in this room is affected by what goes on outside, but it's a very, very good approximation. In quantum mechanics, we have a Hilbert space, and in quantum field theory, we can actually decompose the Hilbert space using a basis of some fields that are only vibrating outside and some other fields that are only vibrating inside. So that's to say that the Hilbert space can be factorized into a Hilbert space of modes inside the room, and the tensor product of that with the Hilbert space outside gives us the whole state of the universe, the space of states of the universe. And then telling you what's inside, what the density matrix of the world is inside this room, tells you absolutely nothing about what goes on outside. And again, there might be subtleties with quantum gravity, because there can be constraints, but they certainly don't come anywhere close to determining what is outside. So the naive view that just because I have a photograph of a deer or a memory of a deer means there's probably a deer out there cannot possibly be justified just by the present state of the world and the laws of physics. You need more than that. However, you might say, well, maybe even if it's not rigorously the case that a photograph of a deer implies the existence of a deer, maybe it's probably the case. Maybe there is some statistical argument that you can make. So when we say that, which I think is true, that the image of a deer here gives us no good reason to think there's an actual deer out there, that is assuming some kind of measure on the space of possible states outside the room. Even given this decomposition, maybe it is the case that the measure is highly peaked on things with correlations between there and there. Yes?
Shane, what exactly do we have inside the room regarding our own conscious state? Then our macro state, presumably.
Yeah, I'm imagining that we have all of our conscious thoughts. So I'm imagining that we could take the time and write down every conscious thought and memory that we have in our brains. And that's what we have. We don't really write it down, but we have access to it. There's a little box in our brain that is full of memories, and we can just pull any of them out. That's what I'm giving you as part of the memory.
So just me thinking this now on these.
That's right. That's fine. Yeah.
So, so I'm in a room, I look out and I see a deer. So there are these views of knowledge, the architecture of knowledge, we call them like moderate foundationalist views, which would say, look, this experience I have serves as sufficient epistemic justification, knowledge-conducive justification, for the claim that I actually know that there's a deer out there. All these other considerations notwithstanding, it's just basic in my noetic structure, given this vertical experience. So the experience itself sort of provides me with a kind of non-propositional evidence for my belief that there's a deer outside. So I'm just confused I'm confused about the claims that these kinds of considerations are somehow necessary for us to know about the external world or the world outside of the room.
So what I'm saying is, in the case where the shades are closed, and you're not looking at the deer, but you remember having looked at the deer, then that argument that you just gave is just false. That is not enough to guarantee that there's a deer out there, or even give you any reason to believe there's a deer out there.
So these views in the architecture of knowledge make room for having as basic foundational justification. You can have basic justification for memory-based beliefs. The fact that I remember, the fact that I recollect in a particular way is enough to yield knowledge-conducive epistemic justification for my belief that I had such and such experience. So I'm just thinking that we have to sort of get off the train with respect to this group of views in epistemology.
That's right.
Okay.
I'm saying that if all you have is this,
okay,
then those views would be incorrect.
Okay.
Now, you can fix them. You can derive them by, as you know, you just impose the past hypothesis. And then you can try to show that when you impose the past hypothesis, there are correlations between what is inside your brain and what is outside. But at this level, we haven't done that yet. So anyways, what I was saying was, so you might hope that maybe some measure on the space of states has the property that when you think that there is a picture of a deer, the memory of a deer, then there's probably a deer. And there are measures with that property, but those are not the measures that sort of the physics itself gives you. And sometimes people say, I have no idea what the measure on the space of states should be. And I think that's too fatalistic. I think that there is an obvious measure to use. There is, in classical mechanics, the Liouville measure. Or in quantum mechanics, there's a quantum mechanical version of it. This is just a measure on the space of states that is conserved under time evolution. So in classical mechanics, if you have Q dot is the derivative with respect to P of the Hamiltonian, and P dot is minus the derivative with respect to Q of the Hamiltonian. Or in quantum mechanics, obviously you have H psi I d by t psi. So you have unitary, reversible, deterministic evolution laws for the states, and those evolution laws preserve a certain measure of the space of states. And that is the only measure that is sort of handed to you by the math itself, by the dynamics of the theory itself. You might have extra considerations, but the theory itself allows for a whole bunch of things to be happening outside here, the overwhelming majority of which do not have any correlations with what's going on in your brain or your memory or your history books or anything like that. So, is it possible that that is right? Is it possible that that is all there is? Is it possible that we, even granting that you're all here and I'm here, that our impressions in our minds that there are other people out there are just false? And it's possible. I think it is logically conceivable. But as David has also argued, it is what we call cognitively unstable. So if you try to take seriously the skeptical point of view that I only believe things that are implied by the laws of physics, I understand them. And those laws of physics, as I understand them, say that anything could be going on outside. It probably looks like thermal equilibrium in one way or another. Then among the things that you don't have a right to believe is your knowledge of the laws of physics that you use to derive that conclusion. The laws of physics just randomly fluctuated in your head with overwhelming probability. They did not actually arise from carefully done experiments. So what that means is that this scenario could be true, but it cannot be simultaneously true and justifiably believed. Now, again, that doesn't mean it can't be true. It just doesn't mean, it means, I'm willing to say, therefore, we shouldn't believe it's true. We should try to do better. We should try to fix it up somehow. And we know how to do that. We add in the past hypothesis. So if this is time, we say that sometime back here, the entropy was much, much less than the entropy now. I don't even have, David, do you have a favorite precise formulation of the statement of the past hypothesis?
No, it's something that remains to be determined, by observational cosmology.
So, roughly speaking, the past hypothesis is the idea that in the past...
it's clearly more than that. It's clearly more than just that the entropy was...
That's right.
There are lots of ways the entropy could have been low that wouldn't do the trick.
Exactly.
Right.
So, the past hypothesis says that at some time in the distant past, the entropy of the universe was very, very low in such a way that natural evolution from that would be compatible with us finding us here with pictures of deer in our heads and so forth. And then you can try to construct an argument, which is certainly not my job right now, that given this past hypothesis and our knowledge of what's going on in the room, there are probably deer running around outside. So again, I'm saying that's not my job to fill in. I mean, there's an enormous amount of work to be done in saying what that gets you. The laws of physics like this, plus the past hypothesis. I'm personally extremely optimistic that it gets you everything you want. It gets you the asymmetry of knowledge between past and future, the asymmetry of causal efficacy, making choices toward the future, et cetera, et cetera. But I leave that to higher pay grades than myself. Instead, what I want to ask is, are there any questions about that? Yeah.
So just a quick question of it. So is the past hypothesis some sort of like relative to, if we assume like a multiverse background, this is, or like a background space-time, this hypothesis is peculiar to our cosmos. Right?
That's right.
This
is our past. Okay. Yes. So, but that's a great question, because that's exactly what I would like to talk about is, so the measure that you you would get from the dynamics itself, if you believe that and nothing else, gets you in some sort of justificatory catastrophe about your belief in the external world. You can fix it by imposing the past hypothesis, but there's no question that regardless of the truth value of the past hypothesis, it seems different than the other laws of physics that we know. So the question is there some cosmological theorizing that we could do, some model we could build, some picture of the world we could have, that implies a different measure than the naive Liouville measure? I like to call this a Sagan-like universe after Carl Sagan, because Carl Sagan never thought about any of these things, as far as I know. But he does have this wonderful, he had a way with words, and he has this pithy statement. Sagan said that if you want to make an apple pie, you must first invent the universe. So I'm not exactly sure what he meant by that, but I think I know what he meant by that. I know one plausible interpretation of that, which is the following, that if you want to make an apple pie, you need apples. Right? You need dough. You need sugar, which means you need sugar cane and apple orchard, which means you need a biosphere, which means you need the earth and the sun, and etc. So an apple pie, Sagan is saying, is not, is contingent. It's relying on all this extra superstructure around it, including in the past. But the point is that this analysis shows that Sagan was wrong. That if you want an apple pie, all you need is an apple pie in thermal equilibrium. That is overwhelmingly the most likely state of the universe, given that there's an apple pie, the rest of the world has no reason to do anything else than be in thermal equilibrium. So what we want to do is to discover cosmological models for the whole universe, what we see and possibly other things, with the property that Sagan was right, with the property that the existence of apple pies is not generally correlated with an external thermal equilibrium, but it's correlated with the existence of apple orchards and sugarcane and things like that. To put in less colorful terms, that when there are rooms like this, then it is probably true that our pictures of the outside world are reliable, are accurate. So maybe there is not just a Liouville measure, maybe there is some cosmic realization measure. Which means that in the actual world, we don't sample every point in state space equally often. The actual world runs through certain configurations more often than others, and it shows that when you get rooms like this, it's usually because they evolved from the low entropy past. And it might not be possible. So I want to get this, since it's a half philosophical audience. Sometimes I or other people in excesses of enthusiasm say that the fact that the early universe is low entropy is a crisis, a challenge, we need to explain it in some way. And, maybe it just is what it is. Maybe it's just nomological. Maybe the early universe having a low entropy is just a fact that we've discovered and we're done. But from a physicist, working physicist's point of view, the fact that the early universe has such a low entropy is taken as a clue. We know that we don't understand the fundamental laws of physics perfectly well. We know there is something to be learned. We don't think we have a complete theory of cosmology yet. The fact that there's something unexpected or weird or unnatural in some measure about the early universe suggests that maybe a way to make progress is to try to explain this fact. That attempt may or may not succeed, but that's the motivation. So it's a clue to try to do better, and we're trying to do right now.
Just some clarification.
Yeah.
So the dialectic here is that, well, this load you said is extremely improbable. Sometimes people make that claim. You're not
It's
making
extremely
that
small measure.
Yeah.
That's all.
You're not. Yeah. You're just saying it's unnatural, and that's enough to motivate thinking about explaining.
It's extremely small measure.
Okay.
And since I don't know why it would be, I'm trying to explain it. Yeah.
Well, we had a very flat-footed response, which just says, look, at some point we're going to have to posit some kind of initial state, perhaps. Work out this kind of picture. We're working on this kind of picture of explanation. We're going to explain future things in terms of past things. At some point, there's going to be something like that. Explain. Tell me more about why I should care that under some measure, even a very natural one, this seems kind of surprising world.
Yeah. No, again, that's a legitimate point of view, as John Maynard Keynes once said. In the long run, we are all dead. So why do we care about anything at all? It might be true that the best version of physics and cosmology that we can possibly ever come up with simply includes a line that says we went through a state of low entropy like that. But it's not obviously true that that is the case. In fact, so what I was going to say right now is it's not obviously true there is a quote-unquote initial condition at all. So that is absolutely on the table, it might be, but I just want to try to do better. I think we can probably try to do better.
So it's really based on like an open possibility kind of motivation as much. I
Yeah.
like the strongest case for motivation.
That's right. The strongest case for motivation is that by looking for scenarios, models, paradigms, whatever you want to call them, in which this naturally happens, or in which this is not a surprise, we might learn something about cosmology. That's the motivation.
I think you can make the case a little stronger. I mean, there are various things that you can push and pull in the theories that we have, and this is like a particularly inviting one compared to the other things that you can push and pull.
Yeah, it's kind of quantitatively a bigger clue than most. That's fine. That's fine. I mean, numerically, obviously, the entropy was enormously low compared to what it is. All right, so now we reach the stage of the talk where, as I said to Bill before, I could shuffle all these pieces of paper and they're already in equilibrium. It doesn't really matter what I say in what order. I'm just trying to get a few things on the table here. So, one idea is this notion we just mentioned of eternity. Or, should I spell it wrong?
It's R-N, I think.
Man. I can't even claim jet lag, right? In the way that everyone in this room was brought up to believe the universe works, there is a moment 13.8 billion years ago which we call the Big Bang. And we know the Big Bang is a place where we don't understand what's going on. Nevertheless, classical general relativity says that it's a boundary to space-time. It's the beginning of the universe. And certainly when they talk to popular audiences, cosmologists often talk as if this is a true fact about the universe, that it began 13.8 billion years ago. There's close to no justification for that statement. The true statement is that 13.8 billion years ago is where we have no clue what happened. It's possible that it was the beginning of space and time, but it's also possible it was not. So I like to sort of think about it. This is my favorite equation in all physics. The Schrödinger equation. I like it so much I will write it down again. So the reason why I'm writing it down again is because if you want to think about the ultimate laws of physics, certainly most physicists would say that quantum mechanics captures something closer to the ultimate laws of physics than classical general relativity does. The world is not classical at some deep level. It seems plausible that, well, one of the possible ways that future physics could go is that this equation is exactly true. That there is a space of states, a Hilbert space, there's some Hamiltonian on this space of states, and classical general relativity arises as some emergent approximation in some particular limit. If that is true, then time does not have a beginning or an end. There's no special thing. You can't run out of time. T goes from minus infinity to infinity according to this equation. The difference is that in classical mechanics, there's similar equations, but the space of states could have a complicated shape. You could hit a boundary or a singularity. That's what happens in GR. In quantum mechanics, there's nothing special about the space of states. You just go in a little circle in any energy eigenstate, in any combination of energy eigenstates, you go in a little torus. There's nothing special about any point in state space compared to any other point, so it can't stop. So if this is true, then the Big Bang is not a boundary. It's just a point where the classical description of space-time may become less relevant. But the quantum state just keeps evolving. So I think that that's absolutely on the table as a possibility. Many of you might have heard that in quantum gravity, we often study the Wheeler-DeWitt equation, which is just saying that we live in the zero energy subspace of Hilbert space, where h psi simply equals 0. Big difference between this state and this equation and this one is that there's no time in this one. And we think there's time in the room, so what's going on? And some people have done some work which is sort of halfway convincing that in this picture, even though there's no time variable, there can be emergence of time. That you could write some variable as part of the Hilbert space where this Hamiltonian that sets psi equal to 0 can be written as some other Hamiltonian minus I d by dt. And then you just get this equation popping out. But that approximation only works in a certain regime. So in that case, time would not necessarily be eternal. It's an emergent approximation, and it may cease to be useful at the moment we call the Big Bang. In which case, I think you would not be able to do better than just what you said, which is you put some initial conditions on and you declare victory. But if this is the case, then you can put conditions at any one moment in time, but any moment is just as good as any other moment. So you would have to explain what was so special about the Big Bang moment versus today, for example. And this, of course, this equation is suggested by taking classical general relativity in a cosmological context, so either a closed universe or an open homogeneous universe, and quantizing. Then you get h psi equals 0. On the other hand, you don't always get h psi equals 0 if you're not in that context. For example, the context in which we best understand quantum gravity is ADS-CFT. And you're all experts on ADS-CFT now, right? That happened? Your expertise came into existence over the past 2 weeks? All right, well, long story short, the only place where we really claim to have a decent understanding of quantum gravity is in an anti-de Sitter background. I'll tell you what that means in a second. But it's a case where there is a duality. This theory of gravity, this cosmological theory with gravity, is supposed to be exactly equivalent to a quantum field theory without gravity in flat spacetime. And that quantum field theory without gravity has a Hamiltonian, and it is not zero, and it undergoes time evolution. So in the best understood example of quantum gravity is this equation that is true, not that one. So this one might end up being true. It's on the table, but it's not demanded by anything we know about gravity in any case. Yeah?
So I actually have a comment on the point you made about how there's a sort of like hope expressed that, look, when we come to understand gravity fully and completely, in the sort of like full context of a quantum regime, we're going to give up on this idea that sort of like Big Bang event was the beginning, right? The beginning of time, right? So I mean, I know you're aware because I've seen you cite the Boyd-Guthrie-Lincoln sort of like theorem, right? And Anthony talked about it in a previous talk. He suggested, look, there's a way to skirt around this. What you do is you just say that the space-time you're working in is a pure de Sitter space-time. And it's sort of well known that that kind of space-time is geodesically complete, and so, you know, the BGB just isn't going to apply, at least straightforwardly. But, I mean, no one sort of, so far as I'm aware, no one's saying that our cosmos is pure de Sitter. It might be symptotically de Sitter at the later stages, but as of right now, what would describe our cosmos is a sort of like Friedman, Lemaitre, Robertson, Walker. And so, I mean, even on your model with Chin, you've got an eternally inflating space-time region, and the Hubble constant is going to be on average greater than 0. And so the BGB theorem is just going to be straightforwardly applicable to our space-time, to our cosmos. So there's sort of like no skirting around an initial boundary by appeal to a de Sitter space-time, because that's not our cosmos.
Right, but that's not how I skirted around it.
Okay.
At its most exaggerated implication, which is not accurate, but sometimes people take it to be accurate, the Boyd-Guthrie-Lincoln theorem says that under certain assumptions there's a singularity in the text. Even that's not right. But
But
imagine even that were right. What I'm saying here is that that does not mean that there's a boundary. All that means is that the classical space-time description fails.
So I think there's a disagreement between you and I about how to interpret the theorem. I mean, so Lincoln's just recently authored a paper where he says, look, our theorem wasn't the singularity theorem. What it does in fact show is that there is a past boundary, the very thing that it seems you're trying to escape.
It can't say that because it's a theorem about classical space-time. It's not a theorem about the quantum state.
So I was under the impression that the theorem has sort of like no robust classical assumptions, that there's just this one model-independent assumption regarding...
It doesn't use classical equations of motion, but it's a theorem about space-time.
Right.
What I'm saying here is that space-time might not be the right way of talking about the universe. That's the implication. Not that space-time ends.
So I guess you're saying that those theorems have exactly the same kind of status as the Penrose-Hawking singularity theorems in classical geometry.
Yeah, when you hit a singularity is exactly when you should stop talking about space-time. Not when you should say space-time ends. It's when you need a better theory. And I don't know what that theory is. That theory might let you go through the singularity, it might resolve it, you know, there's many things that could happen. But it's zero justification for saying that is a boundary to the universe within what we currently know.
One other real quick follow-up. Would you say that the theorem at least gives you past null geodesic incompleteness?
In space-time.
Right. In space time. Right. You would say that.
I'm saying that this is exactly a regime where you shouldn't be talking about space-time. Space-time is overrated. And I say this as someone who wrote a book with the word space-time in it. And of course, there's the final possibility, which is that you need to go beyond quantum mechanics in any form whatsoever. Obviously on the table, but I don't think it's yet called for by things we understand, so I'm not going to think about that. So in other words, all I'm trying to do here is justify the fact that I am going to pursue this idea, that there isn't a beginning or end to the universe, that every state implies both the future and the past equally well, and it obeys something like Schrödinger's equation or some deterministic generalization thereof. Now, another thing that is sometimes an issue, all right, I can erase this. Sometimes an issue, again, we're just still doing trope theory here. There's a theorem that says as soon as you erase something, you need it. So the fact that the early universe, there's a past hypothesis and that our conventional formulations thereof include something along the lines of the early universe had a low entropy. Sometimes bugs people because in the context of gravity, we don't have a once and for all definition of what the entropy is. So certainly in my mind, when I use the word entropy, I almost always, not always, but almost always use Boltzmann's definition. It's on his tombstone. It should be the goal of every working physicist to get an equation of some sort on their tombstone. Hopefully one that they made up, but if not, you're welcome to use this one. Boltzmann will. So the point of this equation is that there is a space of states. There is some coarse graining on the space of states, or sets of equivalence classes under which different states look similar macroscopically, whatever that means. Then you take the volume of those states and you take the logarithm, and that's the entropy of the state that you happen to be in. In quantum gravity, or even in classical gravity, we don't have a very good understanding of what the space of states is. So we cannot straightforwardly apply this equation. So people worry that maybe you shouldn't have this conversation because you don't know what entropy is. So, number one, I think I do know what entropy is more than well enough to have this conversation. But number two, I claim I don't need to. And so let me just spend a few minutes convincing you I don't even need this to make the same intellectual point. So I'm worried, should I even do this? All right, let me do the short version of this argument. What the argument is that we do understand GR, classical general relativity, in the weak field classical regime. So there is a measure, the Liouville measure, in classical general relativity. And that measure is more than enough to make the case that in this measure, the number of states that look like our universe is infinitesimally tiny compared to what it could have been, even with some conditionalization over the present universe or something like that. So the Liouville measure is a measure on the space of classical states, which is the measure on phase space, some collections of P's and Q's, momenta and coordinates. And it just takes the form, you sum over all of the different indices for each particle or for each dimension of configuration space, I equals 1 to n, d, t, I, e, q, I, and you take the whole thing to the nth power. I'm not writing there because I'm not going to give you any homework, but there's an equation, okay? There really is a measure, I'm not just promising it. And I'll say this in words, in cosmology, we don't care about the measure on the space of states. Maybe we care, but that's not what we're interested here in this particular problem. It's not like a glass of water or something equilibrating in real time where you want to find out what most of the states look like because you wait until it equilibrates. The universe is not equilibrated or anything close to that. What we want to know is has the history of our universe been in some sense typical, or is it some sense small in the space of possible trajectories? So we don't want a measure on phase space. We want a measure on the space of trajectories. So there's a paper in the 1980s by Gibbons, Hawking, and Stewart where they did this. these two facts. Number one, you go from this, the phase space is 2n dimensional. If you have n configuration space variables and n momenta. So the space of trajectories is 2n minus 1 dimensional. Just like that. The dimensionality of the space of trajectories is 2n minus 1, because every point defines a line. But there's also, in general relativity, there is the Hamiltonian constraint. So there's an equation of motion, there's a variable in the Hamiltonian or whatever, which has no conjugate momentum. So its equation of motion is simply a constraint. Some possible trajectories are unphysical. They don't satisfy the constraint. So the dimensionality of the physical trajectories is 2n minus 2. And what Gibbons, Hawking, and Stewart do is take this measure and bring it back to this lower dimensional space, the space of physical trajectories. And it's absolutely unique. It's as unique as the Liouville measure. Okay? It is telling you that in the space of classical general relativistic solutions, I can count how many look a certain way versus how many look another way. And if you apply this to cosmology, again, in a regime where you don't need to talk about entropy or coarse graining or anything like that, you can apply it to the situation which we think is physical, which is an expanding Robertson-Walker universe with small perturbations to it. Yes?
Is there an intuitive explanation for why limiting to just the physical trajectories takes the dimension of that trajectory space down by 1?
No. It's not even true. There are other constraints also, but you generally make an ansatz for the particular kinds of quantitative investigations you're doing here. You're doing cosmology. So you start with a homogeneous and isotropic cosmology, and you look at perturbations of that, and the other constraints are automatically satisfied. So given that ansatz for the metric, there happens to be one physical constraint you need to apply. But I don't know a simple back of the envelope intuitive reason why.
Because the first step, going from the phase space to trajectories, makes perfect sense.
That makes perfect. I admit it. Yes, definitely.
Okay.
It just works out this way. I mean, it's not at all obvious that it should work out, but it worked out. So what can we do with this? So the two things we can do with this. One is we can look at Robertson-Walker universes, which is to say universes that are homogeneous and isotropic. So these are universes that have a scale factor, A of t, and there's some curvature parameter, kappa, the spatial curvature of the universe. If it's 0, you're Euclidean. If it's negative, you're saddle-shaped. If it's positive, you're a sphere. And there's something that's famous in discussions of inflationary cosmology called the flatness problem. The flatness problem stems from, you define omega k. Omega is the density parameter of the universe, which equals 1 if the universe is flat. If omega is less than 1, the universe is negatively curved. If it's greater than 1, it's positively curved. Omega k is 1 minus omega. It is the difference between the actual density of the universe and the density you need to make it flat. And in terms of the curvature parameter kappa, it is minus 3 kappa over a squared h squared. And the point is that omega k, if you define omega matter, for example, omega matter is 8 pi g over 3, rho matter over a squared. No, over h squared, sorry. So the ratio, omega kappa over omega matter, is proportional. The h squares cancel out, and it's proportional to, let me get it right, a to the minus 2 over rho matter. But rho matter goes as a to the minus 3, so this goes as a. Which is to say, in an expanding universe, the ratio of curvature effectively to matter increases with time. Therefore, if in the early universe, you say if this ratio of curvature to matter were of order 1, then it would be huge today, because A has increased by some enormous factor. The universe has expanded by a lot since the early universe. That's the flatness problem, because omega k really is very small, order percent or less. It had to be very, very, very small, 10 to the minus 60th or something like that at early times. And how unlikely is that? That is the flatness problem. The flatness problem is a lie, completely fake. Because the question, how unlikely is that, is it's actually very, very likely. How do I know that? Because there's a measure on the space of trajectories, and I can plug it in. And the measure looks like d mu is proportional to the absolute value of omega k to the minus 5 Pascal. Which is a way of saying that if I plot it versus omega k, it looks like this. And in fact, it's the integral diverges near 0. For any epsilon that you choose, there is a finite amount of probability or measure outside that epsilon and an infinite amount of measure inside. So for any curvature that you might have picked in the early universe, there's probability 1 that the real curvature is less than that in this measure. Now, you might say, well, I don't like that measure, I don't want to use it. That's okay. There's no justification for using this measure other than it happens to be what the math gives you. The point is there's also no justification for saying that omega kappa over omega matter should be order 1. The closest we have to a justification says that omega kappa should be 0. So you should not be surprised that the universe is prime. I mention that only as sort of amusing aside and a reminder that measures are not easily guessed. You need to actually do the work. Maybe you don't have any, you say we don't have any measure at all, but when you have them, you should actually use them, not just guess your favorite one and then make a big foo-for-all about how the universe is unnatural in the measure that you just made up. The other thing you can do, any questions about that? Everyone's perfectly happy with my statement that the flatness problem is a lie, really? Yes?
I have two questions. So in that paper, there is no assumption about the metric, right?
Which paper? There's no assumption about the metric.
About the assumption if it's a Friedman or a Hawking metric or not.
Oh, well, I mean, that's true. They write down a measure.
I'm asking because if they assume this already, then it goes into their argument about the one. So it doesn't go into it. About K, they don't make any assumption.
This argument only makes sense if you assume Robertson-Walker.
Yes, but the other one. I'm asking the other one.
Because
you use that measure. For that measure, there is no assumption made about the metric.
No, I think you can do it for any kind of metric.
Okay. And then the second thing is how do you ensure that even if you start out with a flat universe that your k doesn't grow, because if you write down the a² equation, then you have a k over a².
Yeah.
And if this factor is not suppressed by the other factors, it can still grow so that you end up by an open or closed universe.
That's right. So that's exactly what we're doing here. So we're allowing this term in the Friedman equation to be whatever you want, but we're saying that the trajectories of Friedman-Robertson-Walker universes for which omega k is not equal to 1 are a set of measure 0.
For any initial condition.
Sorry, for omega k is not equal to 0. No, there's a measure on the space of initial conditions. A measure on the space of trajectories is equivalent to a measure on the space of initial conditions. So the initial conditions are infinitely peaked at flat universes in this measure, yes.
So if that's the case, then it seems like the dynamics are not part of it at all. Like you would expect that the universe would be flat at the beginning and it would stay flat forever.
Exactly.
So that doesn't seem to make any sense in terms of the way we understand trajectories.
No, it's just a feature of GR that if you are flat, you do stay flat forever.
Is it really? That seems like a pencil balanced on its tip, and it would be unstable to any sort of perturbations.
There's no question of stability. The stability question is if you move a little bit away from flatness, the deviation grows with time. That's right. But this is saying that all but a set of measure 1 are exactly flat.
But you need to assume an isotropy all the time. So
You assume a Robertson-Walker universe.
parameter, then it would grow such that.
Yeah, that's what I'm going to talk about
it's
next.
Oh, sorry.
So yeah, following up on that, the FRW assumption is only for very large scales, hundreds of megaparsecs.
Yeah, that's right. I'm just trying to take the flatness problem at face value. So you can say that the original discussion of the flatness problem assumed this and this and this. Absolutely yes. But by its own standards, it is wrong.
Okay, I see. But you would agree that in a universe that is not perfectly FRW on the scales of galaxies, that would
I'm going to get to that in a second.
Okay, sorry.
Over here, there's something. Give that?
Just a small, I mean, there's been a little bit of discussion of this actually earlier in this workshop. There's a similar kind of debunking you could run through of the horizon problem. I know this from Shelley Goldstein. Look, you have two chunks of gas or plasma or something here and here. On the standard statistical mechanical measure, if you don't know anything about the relationship between their temperatures, what would you expect it to be, independent of any causal interaction? Well, the relation between their temperatures consistent with the highest number of microstates is where they're equal.
So there's two things. Number one, that's wrong.
It is
Number-
wrong.
number
It's
two-
important to emphasize that it's wrong. I emphasized it the first week when Shelley was here, and I keep hearing David just repeat the same nonsense. It's really
It's wrong
annoying.
because the universe can expand. So there's enormously more phase space to take that box of gas and expand it by a factor of a bajillion and make its temperature zero.
So I'm sure what you're saying is.
You're not allowed to fix the volume.
Say it again?
You're not allowed to fix the volume because it's general relativity.
Oh, no, but you have two chunks of gas early in the history of the universe.
Well, who says they're early? What does early mean?
Or you have two chunks of gas that you see now.
Well, are they chunks of gas whose states I am allowed to choose?
Somebody wants to justify the claim that it's surprising that they have the same temperature. Good. How does the argument go? That it's surprising that they have the same temperature.
Let me give you what I think is the correct argument, and then we can talk about. I don't want to spend too much time talking about arguments that are correct, but we can talk about those in this discussion. Okay. So I agree that the way the horizon problem is usually presented is wrong.
Okay.
But I think the conclusion is right. Unlike the flatness problem, which the conclusion is just wrong. The horizon problem is really a smoothness problem. It's really the problem that the universe is homogeneous on large scales. And you can apply this measure to that question, because you can take this Robertson-Walker background, you can perturb it a little bit, and you look at the measure on the space of perturbations. So ordinarily what we do in cosmology, we have the scale factor growing and some way of characterizing the perturbation. There's a second order differential equation that governs the evolution of the perturbations. And you can write down any solution as a linear combination of a growing mode and a decaying mode. And this is true for every Fourier mode. So you take the perturbations, you take the Fourier transform, you look at a fixed wavelength that is growing with time, so a co-moving wavelength. And every wavelength obeys the second order differential equation, and its solution will be a combination of growing mode and decaying mode. And what you always do in real world cosmology is to ignore the decaying mode. Because you say, well, perturbations have been growing. But the point I'm making is that that's because of the past hypothesis. That's not because of physics. It's not because of the laws of motion. So for example, what you can do is say, well, imagine that I believe that the CMB was smooth. So there were fluctuations of order 10 to the minus 5 at recombination. Again, we could argue that I don't think that's necessarily implied by anything, but let's at least grant our conventional cosmologists that much, because they do believe that it's true. But let's not grant them the right to turn off the decaying modes, because there's nothing observationally that says the perturbation modes at recombination were either decaying or growing. That's just an assumption. If you unmake that assumption, you have the ability to include both growing and decaying modes. And you have a measure on the space of it. And you can ask, given this, this freedom that you have at the CMB, at recombination, in the early universe, at the gut scale, for example, what is the chance that the perturbations were less than order 1? What was the chance that the universe was still smooth back at the gut scale? And the probability of early smoothness given CMB smoothness is less than 10 to the minus 10 to the 7 or something like that. It's just one of these preposterously tiny cosmology. And of course, I could do the same thing. The reason I chose the CMB is because then almost all the early evolution is radiation dominated and it's easy to solve the equations. So this is a paper I wrote with Haywood Tan a couple of years ago. The point is you do the same thing today. You could say, if today the perturbations were 10 to the minus 5, what should they have been when the CMB was formed? They should have been cubed. The measure, so this is what I would say to David is the correct way of stating the horizon problem, the smoothness problem. Given anything we know about the universe today, in this well-defined measure, the overwhelming majority of cosmological histories were extremely inhomogeneous in the past. And they have, there were spooky correlations between them that smoothed them out as time went on. Yeah.
So before you were just talking in terms of metrics, and now you put it into a probability.
Yeah, I shouldn't have done that.
Okay, so you're still talking about
Me.
this.
Good catch. Sometimes I'm careful and sometimes I'm not. That is right.
But I mean, some people do want to then extend this to the
I know.
probability, and this is, yeah.
Exactly. Right. Okay. So, unlike the flatness problem, I think that the moral lesson is that most cosmological trajectories are highly inhomogeneous. There's no reason for the universe to be anywhere near smooth, and yet it is. Why? Because of the passive hypothesis. That's why it is in one version or another. So the point here is that I didn't use the word entropy anymore. I stuck to the regime where I understand how gravity works. It's classical general relativity. There's a well-defined measure. Most trajectories don't look like the universe in which we live. That's a clue that maybe there's something to be understood. Yes.
So have we sort of intentionally and purposefully sort of delimited ourselves to the CMB smoothness in the measure here?
Only
Or is
picked
it
this.
just in general what we know about the cosmos superiorly in general?
It's pretty general. The numbers would be different if you pick some other epoch. But the point is just that there is no reason, even given smoothness in any one era, to imagine smoothness in any other era.
Okay, good. Because I thought that there were some theorems which tried to move from particular facets of the data we have on the CMB to sort of like general judgment about the nature of the space. That it was, in particular, Friedman, Lagrange, Robinson, Walker. So there's the Ehlers, Guerin, Sox theorem, which
Yeah, I think the lesson here is just that there's no reason for perturbations to be small, given what we physically know about
Okay.
the
Okay.
universe.
But Sean, and maybe this will just have to be discussion for after. It's not the case that the probability or the measure for later smoothness given early smoothness is high. That is, it's not the case that early smoothness tends to induce later smoothness.
Obviously, if the early smoothness is smooth enough,
Right.
then you get later smoothness. That's the
Right.
real world. Yeah,
Right.
that's right.
Right.
So the expansion of the universe acts as a brake on the growth of perturbations.
Right.
So when I said growing modes, it actually is dependent on the equation of state and stuff like that.
Right.
The point here is that if in the collapsing universe, the collapse acts as an acceleration of the perturbation growth.
Right.
So you would generically, even given what we understand today about the universe, expect the early universe to be very, very inhomogeneous, and it's not.
Okay, I'll
Okay.
So in talking about the very early universe, you're limiting yourself to just the GOT scale, for example, where you think that classical GR is good enough.
Yeah.
So would a kind of an explanation that would work for you be if in a theory of quantum gravity we actually found that a different measure is appropriate and if quantum gravity really does predict that generically things are smooth?
Well, that's an excellent question. Thank you. I should have mentioned that. Obviously, if you add to your theory a theory or a statement or a rule about initial conditions, then this measure is worthless. This measure is not telling you anything at all. So, yeah, you can get away from all these conclusions if you actually have a theory of initial conditions. This is just a statement about can you get out of the theory of initial conditions through the dynamics, and the answer is no. Okay. And in particular, you might imagine that even classically, maybe we don't know the laws of physics in the early universe, so maybe they could act as an attractor, right? Maybe they could push the universe to something that looks like it does today. This measure, this construction by GHS, proved that that is never possible. And the reason why is because, I was trying to hurry so I didn't actually say this. The way that you evaluate this measure on the space of trajectories is you take a hypersurface through them. So you say, for example, all times, all moments when the Hubble constant is some fixed value. Okay, and then you look at the different possible configurations of matter and energy and perturbations and so on. And the point is that the measure is invariant under which hypersurface you choose. So the fact that the measure on smooth trajectories is small today means there's no possible choice of Hamiltonian in the early universe that makes that measure big. We're done. It is small for some reason. You cannot explain that smallness just by unitary laws of physics. You need something else. Okay, now.
Just one, there's also, I forget if that's the GHS paper, there's a later paper where it's including coupled with scalar field, right?
Yeah,
So the same result holds even if you throw in a scalar field.
there is a scalar field in this calculation, because you need something to be that phase space degree of freedom, one way or the other. Here in the perturbation calculation, the amplitude of the perturbation is your extra phase space degree of freedom. Here it is some sort of scalar. If it's just pure GR, then there's not that much you can do. All right. Let's see. So all of that was just to convince you something that you were probably already convinced of, that the fact that the early universe has this certain state is in fact a surprise, in the sense that nothing that we know in the current laws of physics implies that it should be true or natural or probable or anything. You don't need to use the word entropy to make that point, although you can. So what should the universe look like? Now, that's a normative sounding question. I don't know what the answer is. But if you didn't know anything about the laws of physics, what might you guess the universe was like if you didn't actually have any observations of the universe? Well, we can talk about, in general relativity, we can talk about vacuum. We can talk about maximally symmetric space-time. And you might guess that, here's some space-times that are special in some way, that they're not, it's, in some sense, the lowest energy, at the very least, certainly the most symmetric space-times you can write down. And you might have guessed that you live in one of those space-times. So I'm just trying to get some things on the table for later discussions here. So these are solutions to Einstein's equations with a cosmological constant. And you probably know what the answers are. There's Minkowski space, when lambda equals 0. And are you all experts at Penrose diagrams by now? Has that expertise been achieved? See all these?
Well, they've been used. It might be a good idea if you explain the basic idea.
All right. Penrose, is a brilliant guy, and one of the many things he figured out is how to take an infinitely big universe and fit it onto one piece of paper. Okay. So ordinarily when we draw Minkowski space, we say here's X, here's T. They go on forever. There are light cones like this. And what Penrose did is multiply the metric by a function, and a function that gets smaller and smaller as you get very, very far away. That's easy to do. But he did it in such a way that he maintains the shape of the light cones. That's why it's a conformal transformation. So he figured out a way to draw space-times in such a way that it's obvious what the causal structure is. It's obvious where time-like, space-like, null trajectories. And in that way of drawing Minkowski space, it looks kind of like this. So here's time, going forward. This surface, even though it's drawn like a disk, this is a three-dimensional Euclidean space, and it evolves with time. So light cones go 45 degrees everywhere in this picture. Every time-like geodesic ends up here. The other thing to say about Minkowski space is that geodesics neither diverge nor converge. So if you start two particles stationary with respect to each other, they keep the same distance from each other.
Is that for any geodesic or specifically time-like?
This is a statement about particles that are initially stationary with respect to each other. Any time-like geodesic goes to this point. This is time-like infinity, this is null infinity, space-like, past null, etc. Then there is de Sitter space. Hopefully this is repeated when lambda is greater than 0. The conformal or Penrose diagram for de Sitter space looks like a squat little cylinder. And here, these slices, these space-like slices, are actually three spheres. Time goes upward. And the weird thing here is that really, if you think about de Sitter space, a more physically accurate representation would be a hyperboloid, contracting and then hitting a throat and then expanding. So that's true here. What it means is that the geometry is not immediately obvious, right? So this three sphere has a size. Any other three sphere later on is much, much bigger. But I've drawn it at the same size. That's the miracle of the Penrose. And that's because geodesics in de Sitter have the property that they're initially at rest with respect to each other. They tend to diverge with time. Particles get pulled apart by the expansion. And finally, there's anti-decision. And lambda is less than 0. And that one, even Penrose does not succeed in fitting it onto one piece of paper. It goes infinitely far to the past and future. So that's what it does. And what happens there is there's a boundary. So here's a little part of ADS. And here the space-like surfaces are again, topologically, R3, but in fact they're negatively curved space-like surfaces. This is where string theorists who like ADS space get to pull out their Escher pictures of all the tessellations of the negatively curved plane. And in ADS, it's like a box that keeps you confined. So if you have two initially stationary particles, they get pulled together by the negative cosmological constant. So a trajectory in ADS for a time-like free particle looks like this. So if you have a black hole or whatever and say, well, it evaporates and goes to infinity, but it doesn't because all that stuff comes back in some finite time depending on the value of lambda. And there's something to say about perturbation sensibility that I'm not going to say here. So you might have thought that these are natural universes in which to live, and you just go out and measure lambda, and maybe we've done that in 1998, and it's a positive number, and we should live in de Sitter space. That is an attitude you could have, and I will discuss that attitude. To connect that suggestion that no one ever makes because we know it's not true, but I'm just trying to, it's very hard, it's like proving the existence of God, right? It's very hard to be honest about what we would expect if we didn't know what we know. So if you didn't know anything about the universe, what kind of universe would you expect to live in? I think that you would expect to live in one of these, and de Sitter would be the experimental result, but then you'd have to explain why we don't. Yes?
But then if you look at the space of all solutions to general relativity, you find that value is 0.
I'll talk about that in a second. Yeah, to connect to the rest of the discussion, we should talk about entropy. In fact, I should talk first about horizon entropy. I get to go until 3 and then we take a break, is that right?
Right.
I have to slow down, I'm not getting through too much material, but your life will go on, but you're not getting through everything. You'd have the discussion.
But remember,
so don't
you
feel...
then continue after 3:30.
Yeah, oh, I know. I'm thinking about it now. That is very much in my mind. Okay, so any questions?
So, with respect to all three of these spaces that you're thinking are sort of very natural, there's sort of like a Kachi. Well, you're thinking of them all as being symmetric, right? So there's some sort of like global Kachi hypersurface at the middle moment in, for example, the de Sitter space that you marked as S3, and then R3 in the anti-de Sitter space, and then R3 in the Minkowski space. Is that right?
The being in the middle is completely...
This is arbitrary.
Yeah.
Okay, good.
When I say maximal symmetry,
Yeah.
a symmetry, I don't know what your GR level is, but there's a way to quantify symmetries of a metric using killing vectors. And there's a maximum number of killing vectors that space-time can have, and these three space-times each have the maximum possible number. That's what it means to say they're maximum symmetry.
I see. Okay.
So it's a space-time statement, not a spatial slice statement.
They're the only ones that have maximal.
Up to global identifications or something like that. Locally, they're the only ones, yes.
So would you say that it's more probable that empty universe because you have the visitor is nothing?
Yeah, I will get to that. That's an obviously good question, yes. This is, you're not supposed to believe what I just said. I'm just saying, maybe you might guess. Yeah, that's right. I'm going to try to...
You never feel it with this equation.
No one ever thinks that this is even plausible because they know it's not true. You're not going to get tenure by writing papers thinking, I think we should live in de Sitter space, because you know that's not true.
Also, Pochinski model has the same problem, yeah? Because they have a very good model of explaining the value of the cosmological constant at the end of the anti-universe problem. Just asking what is
Yeah, that's right. So that is one of the issues.
Problems where I didn't try, assuming it's empty.
Yeah, I will definitely get to that.
Okay.
Good. Yes.
One other just quick about de Sitter space. So, I mean, at least with respect to that space, insofar as it's going to be hyperbolic, there will be a global calculator service.
Sure, there's many.
I'm
I'm just not using that for anything.
Yeah, okay, cool. Okay.
In ADS there's not, but in those two there are. So, so to get to your question, to put a little bit more meat on the bones of, are these, so they're symmetric, okay, that's fine, but what about, is there some sense in which they're likely, or there's a lot of them, or something like that? They're all unique spacetimes. Classically, they are, like you say, measure zero, right? We should be able to do better. So we should talk about the entropy associated with these spacetimes. And now I'm going to use, so you're all experts in many, many things. So you know that h bar equals c equals 1. And you know that therefore the Planck mass is the Planck energy, is the Planck temperature, is 1 over the Planck length, is 1 over the Planck time. And also I use units in which any number between 10 to the minus 3 and 10 to the plus 3 equals 1. So 4, 5, 16, 137, these are all equal to 1. So we are trying to talk about the entropy of spacetimes. We don't have a complete theory of anything like that, but we have some special cases that we can make use of. And obviously, the most useful special case that Lenny talked about last week are black holes. So here's a black hole. It has an event horizon with an entropy. I'm specializing to 3 plus 1 dimensional spacetime, so I hope that's okay. And so there's a temperature. Hawking showed us that black holes give off radiation. And the temperature, in my units where everything equals 1, can be written as the Planck mass squared over the black hole mass. At least I think this is right. I guessed it on the basis of dimensional analysis. It's 1 over the mass, the temperature. And because temperature has units of mass, it better have a Planck mass on the top. And then there's an entropy associated with that. The entropy, as Hawking famously showed, is the area over Newton's constant. Even I know it's really the area over 4 times Newton's constant, but just to be, I'll draw a little tilde instead of Newton's constant. So in these units...
But 4 is 1.
Exactly, that's why I didn't write it. You can kind of see it there, if you're really careful. So that's the area of the event horizon divided by the Planck length squared. Or if you like to think about things in terms of the mass of the black hole, that's the Planck mass squared over the black hole mass squared. So entropy goes up as the mass goes up, as the mass squared. That can't be right.
You should do it the other way around.
Yeah. Even I, once again,
It ought to be a big number.
It needs to be a big number. What is it in terms of the mass? The area goes as the mass squared.
Oh, yeah.
The black hole mass on the top, squared.
Right. And the
Planck
Planck mass on the bottom.
Mass is on the
Yeah,
bottom.
sure.
Good, because there's a secret factor of the Planck mass to the 4th because of the G. All right. So it's a big number. It's a very, very big number, as we'll see in a second. And there's another, so this is what Hawking showed. There's something that is sometimes assumed and more occasionally argued for, which is that because of this entropy, we should think of the black hole as having a quantum state that is described by a finite dimensional Hilbert space, where the dimensionality of that Hilbert space is the entropy. That's an H. So that should be, strictly speaking, true if the black hole is a quantum system in thermal equilibrium. Then its entropy should be the dimensionality of its Hilbert space. There's even an argument the black hole is in thermal equilibrium. There's an argument about what's called fast scramblers. If you drop something onto a black hole and ask how long does it take for that stuff to spread and equilibrate around the horizon, the answer is really, really fast compared to any other time scale in the problem. So black holes equilibrate very, very quickly. They should be in equilibrium. The entropy should be telling us the dimensionality of the Hilbert space required to. These are all hand-wavy, fuzzy arguments, but this is very much standard lore in the field. Okay, so that's all. That should be received.
And so we went from thermodynamic entropy, black hole entropy to quantum entropy.
Indeed, we did do all that just now. Yes, caught me, but it's true. Right. So at least I'm happy to think of it as Boltzmann entropy. Von Neumann entropy, probably, but this is the von Neumann entropy problem. Yes. Okay, so if you're willing to believe that, there's a similar set of statements you can make about de Sitter space. Minkowski space has no horizons in it from anywhere. There's no point that is causally separated from you. You can always catch up with any of your friends, given enough time. But in de Sitter space, so here is a spatial slice of de Sitter space, a little bit of it. So this is not the whole 3-sphere. This is just part of de Sitter space. And here you are. And here's a long-lost friend of yours, but they're very far away because they went exploring. There is a region around you where people who are outside that region will never be able to talk to you ever again. Because the expansion of space means that no matter what you do, they are being pulled away from you, and even a light signal from you will never get to their future state. So this is a horizon. This is the de Sitter horizon around you. And unlike a black hole event horizon, it's not a fixed location in space, it's a feature of every observer. Every observer has around them a horizon. And if I were to plot it over here, so this is again a little quirk of the Penrose diagram. If I start at the throat, at this 3-sphere in the middle of the Penrose diagram, the null surfaces go like this at 45 degrees, and they meet at exactly a point in the past and future. And if I take these null surfaces and I divide them up into 2 spheres, I foliate this by 2 spheres. Unbeknownst to you, these 2 spheres have the same size. They're constant radius. Doesn't look like that from the picture, but that's because secretly the metric is expanding to beat the band. So the radius of, on this light cone, the radius of all those spheres is the same size. And I even know what the number is. So I didn't write it down. It's got to be like the square root of lambda. What else could it be? Dimension. So that's the horizon. And that exact same, not exact same, but precisely analogous logic to what Hawking used to derive Hawking radiation works for de Sitter space, except that you're in the interior of the horizon rather than outside. So when you're in here, there's radiation coming into you from the horizon. And it has a temperature, and it has an entropy. So, to give you the numbers, the area of the event horizon is proportional to the inverse of the cosmological constant. So low cosmological constant is a big horizon. The temperature goes as the square root of lambda. So once again, low temperature is small cosmological constant. And then there is an entropy that you think of as sort of the entropy inside this horizon. It's a little vague what you mean by that, but we call it the de Sitter entropy. And it's going to look similar equations to that. It's the area of the event horizon over the Planck mass squared, Planck length squared. And that works out to be the Planck mass squared over lambda. So the bigger lambda is, the smaller the entropy is. When lambda is close to 0, the entropy is very, very big. In our universe, the lambda we think is actually real is a very tiny number, so we live in a big horizon with a lot of entropy. So, if you go back here, we don't know how to make this kind of statement in the ADS context. ADS is, despite the fact that it's string theorist's favorite space-time, in many ways it's less understood than de Sitter and Minkowski. Its stability is not as well understood. It's not globally hyperbolic. We don't know how to calculate the entropy. But in de Sitter, we can do this, and you can take the limit as lambda goes to 0, and Minkowski would appear to have infinite entropy. Because Minkowski is lambda is 0. The entropy goes inversely. So, if you were to take, so it's not valid, it would be way too naive, even for these lectures, to simply say, well, here's one solution, there's one solution, there's one solution, there's an infinite number of solutions, none of the solutions will look like that. If you take this seriously, this is saying that there is a Hilbert space describing what's going on inside that horizon, which is finite dimensional, but still a very big dimension. So the number of states is e to the entropy, so it's e to a very large number. So there's actually many, 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 many quantum states that look like de Sitter space. And there's purportedly an infinite number of quantum states that look like Minkowski space. What you want to make of that suggested fact is still not clear, but that's a better way of counting than just to say it's only one classical solution to general relativity. Now, good. Oh yeah, I was right about 1 over root lambda. Okay. I was wrong about 1 over. It's 1 over root lambda. I had a chance. So the last thing I want to say, that I was told you didn't talk too much about.
Actually,
Go ahead, Anthony. Go.
Well, I was curious as to your viewpoint about calling this the entropy of the sitter space.
I don't really have a viewpoint about it. I'm trying to be vague about it because I think that, you know, I tend to think it seems valid to draw a circle around the horizon and say there's a system that is inside that sphere that is accurately described by a Hilbert space of dimension S. That's all I would try to say.
But you probably will agree that it gets tricky then to talk about arguments like which of these is higher or lower entropy, given that there's all kinds of stuff outside.
Yes, that's right. I'll talk about that in just a second.
well, I just wanted to mention that this is the famous 10 to the 120.
Yeah, that will be.
Right, but people should be aware that people sometimes give a completely different sounding argument, saying that the natural value for the cosmological constant is just m Planck squared.
Right.
And it's actually 10 to the 120 times smaller, and this is the same ratio, except it's
Yeah,
playing a
that's
somewhat
right. I think
different
that's
role.
it is very suggestive that.
But it's also important for people to appreciate, I mentioned this at the end of my second lecture, that this is 10 to the 20 times bigger than the black hole entropy.
all
And
these are
10
things
to
I
the
was saying.
40 times, okay, so you're going to get to it.
Okay. But the last sort of conceptual point I want to get before we start plugging in numbers is this thing called horizon complementarity. So we didn't talk about that? There's no much talk about horizon complementarity here? You're not experts on that? Okay. Good. So let's look at the space-time diagram of this black hole. And we'll let it evaporate, and we will, in our minds, we will take the fact that we know, we've already discussed it, namely that singularities aren't really real, they're just parts of space-time where space-time is not a valid description. And we'll forget that we know that for a second. So we'll draw the black hole space-time for an evaporating black hole like this. So this is the horizon, the dashed line. Hawking radiation comes outside the horizon so that the mass of the black hole diminishes until it poofs away in a puff of smoke that is about the size of a few sticks of TNT, I guess we decided over lunch or something. And outside you go, notice that this bit of the space-time looks exactly like this bit. That's not a lot of information to be impressed by, but it's just saying that far away from the black hole, space-time looks like Minkowski space. So this is a black hole in Minkowski space. So, as you all heard, there's a problem called the black hole information loss problem. It is only a problem if you believe, like I do, in Schrödinger's equation. So you believe in unitary evolution of the quantum state from, for example, here is a space-like slice before the black hole was made, here is one after it was made, and they should be able to unitarily evolve from one to the other. The problem is that I can send something inside, and then it can hit the singularity, and how does it know how to get out there? How does the information that I throw inside get to the exterior region? And this is a problem even if I do excise the singularity. It looks like a more global problem than a singularity problem. And in fact, you can say, well, probably it gets out in the Hawking radiation. Right? When the Hawking radiation comes out, that's where all the mass comes out. That should be where the information comes out. And that sounds plausible, except you can do more quantitative things about it. So you can draw a space-like slice that goes into the black hole and includes some of the Hawking radiation. Hawking radiation that came out after you threw your book in, or whatever. And there's a theorem in quantum mechanics called the no-cloning theorem that says that quantum information cannot be duplicated at two separate locations in space. So if you go through the math, what you show is that if this were true, you could always read off what was in the book before the book ceased to exist. So in order for the information to escape to infinity and preserve the unitary evolution of the black hole, it must be possible to duplicate that information. But the rules of quantum mechanics say you can't duplicate that information. So this is a possible, yes?
Is it the idea of before the book ceased to exist, not really well posed once it's crossed?
Well, so yes and no. So that's let me say a few more words. But at the level of this picture, it seems perfectly wrong. So the suggestion needs to be that this picture is even more wrong than you thought. So in classical GR, or even semi-classical quantum field theory curved spacetime, there's nothing weird about the inside of a black hole before you hit the singularity. You know, spacetime can be arbitrarily smooth and flat, and the rules of quantum field theory should be fine. So if you believe that on this slice, quantum field theory works, because the curvature of spacetime is everywhere small, then you run into a contradiction. It cannot be true that quantum field theory works everywhere on this slice, and information escapes the black hole in the radiation. Something has to give. Many people would give up on the information escaping, but a lot of people, including myself, think the information should be able to escape. So complementarity you're all wondering what any of this has to do with the past hypothesis, but we will get there eventually. Complementarity is the statement that you should give up on quantum field theory being true on this slice. And that's very dramatic, because quantum field theory is basically just, quantum mechanics applied to local degrees of freedom. It's really just sort of locality embedded in a particular implementation of quantum mechanics. So it's very hard, it's even harder than the past hypothesis to get a rigorous statement of what complementarity actually means in this case. Black hole complementarity or horizon complementarity. But one way of saying it is that if here is Alice outside, and here's Bob inside, complementarity is the statement that you can't talk about Alice and Bob at the same time. That seems like a very strange form for law of physics to take, telling you what you can and cannot talk about. I think it is slightly more accurate to say that you cannot describe A and B using the rules of quantum field theory at the same time. So what does that mean operationally? A and B not simultaneously be described using quantum field theory. It means that if you're A, if you're Alice, and you're looking at the black hole, everything that is inside the black hole, as you maybe are pointing toward, is encapsulated on stuff going on at the horizon. Non-locally, in some way describing things that we don't have a direct operational way to put into practice, but in any event, not quantum field theory. Some non-local theory on the boundary, on the horizon of the black hole. Whereas if you were B, if you were Bob, you think everything is fine. But you can't actually describe what's going on outside the event horizon using those rules of quantum physics.
I'm just trying to understand what the claim is. The claim is that, for example, that surface, including both A and B, there isn't going to be a quantum state assigned to that surface. Is that right?
It's almost right. Let me put it this way, because I think my guess as to what complementarity is trying to say, which I'm not sure is right, but here's my best way of saying it, is that if you are in a quantum state with the property that A looks around and says, yeah, quantum field theory works, then in that quantum state, B does not look around and say the quantum field theory works. And you might say, well, that can't be right because I can sort of independently choose the basis for Hilbert space here and over there. But complementarity is saying, no, you can't. That once you choose the quantum state outside the horizon, the information
you
of
mean there's
B...
a kind of unitary inequivalence between the basis you would use for A and the basis you would use for B?
I don't think they're unitarily inequivalent. I think that the basis you use for A, if it goes to the horizon, determines the B. Because the information contained in B's quantum state is on the horizon in that basis.
I mean, we're talking here confusingly about A's quantum state and B's quantum state. I'm not sure I understand that. Usually you would assign a quantum state to a say, space-like hypersurface.
Yeah, but what I'm saying is that there's something called the quantum state in which the basis, the pointer basis for that quantum state, in which it looks like quantum field theory. It looks like
there isn't
field.
any such thing as a pointer basis for a quantum state. I still don't understand.
There are observations that A can make. A looks around,
Yeah.
and there is a pointer basis for those observations.
Okay.
And if the observations are such that the pointer basis make it look like it's quantum field theory, that is to say, space-time is pretty flat and degrees of freedom are localized at different locations, then that is not a pointer basis for B, in which it looks like quantum field.
But maybe we should discuss this later too, but I'm puzzled. All of this, the way you introduced it, is being introduced in the interests of preserving the unitarity of the evolution of the overall quantum state.
That's right.
If you're preserving that unitarity of the evolution of the overall quantum state by denying the existence of the overall quantum state, the logic is puzzling.
Right, so I would not do that. What I'm saying is that the quantum state that in the language A would use to describe it doesn't extend inside the black hole. It is a state defined on the horizon and the slice outside. That is sufficient to describe the entire state of the universe. The thing that classically you thought would have been the interior of the black hole is encoded on the event horizon.
Sean, if you put it that way, if you say it's encoded on the event horizon, that still implies that there's a thing which the thing on the event horizon is encoding. That's making it sound as if one way you could specify the state inside the black hole is by saying what's going on the horizon, and in a mathematically equivalent way, you could just specify what's going on in the rest of that space-like hypersurface, but that's not what you mean.
I think that, yeah, I mean, actually that's pretty close to what I mean, except that probably to be more careful, I would have to include a small region outside the horizon. There's sort of a stretch horizon.
If what I just suggested was what you meant, that's committing you to the claim that there is a way to extend the state, that what's being encoded, okay, on the surface is just the proper way to extend the state all the way through the space-like hypersurface. But it's the possibility of that extension that you seem to be denying with the complementarity.
We should probably talk offline a little bit, but and again, this is not clear. So it's not that you're misunderstanding. It's that it is unclear.
Okay.
I believe the claim is supposed to be that in the language where you're A and you have a life outside the black hole and you have a horizon, there isn't any such thing as inside the horizon.
Here's all I mean. You throw one piece of APR state into the black hole. Okay? You want to say the evolution is unitary. Okay? Either you want to say that means that I find a way of that I have a state associated with every point on this hypersurface, and I show how it evolves unitarily. Or I take another option, which is I just deny that the other EPR particle ever got in there, it stayed on the surface, blah, blah, blah.
Right, and the complementarity philosophy says that you can either use a language where it got stuck on the horizon and never made it inside.
Yeah.
Or use a language where it's inside and everything is fine, but then you can't talk about what's going on outside. Good question.
So there's another way of phrasing complementarity that there's no operational way for A and B to synchronize their clocks after B has jumped inside the horizon.
It's much worse than that. There's no operational way for you to make a statement that includes A and B as people with locations in space-time, much less
So when you're talking
synchronizing
about
clocks.
A and B cannot be simultaneously described using QFT, you're not just talking about some simultaneity surface.
Oh no.
You're talking about logically we at the same time can't be
That's
using both notions. Yeah. Okay.
That is the conjecture.
So what happens when the black hole evaporates?
Then quantum field theory is restored outside and you can describe everything.
It's kind of ad hoc.
There is something about the physical situation about the quantum field theory, or you just understand it? Isn't this the way how Lenny wants to solve the fireballs problem, basically?
Yeah, I don't understand
No, I
any
don't
one
want to go into
solution
that
of the
problem
fireball
because
problem. Yeah.
I always have the impression I'm not sure what it tells us. Does it tell us something about the physics, the underlying physics, or about our understanding of physics?
No, I think it tells us something about the underlying physics. It tells us that the quantum state psi of t cannot be expressed as draw a space-like hypersurface, put fields on that surface, look at their perturbations, and look at the Schrödinger picture representation of quantum state of those perturbations. That's quantum field theory, but that is not a good way of talking about the quantum state. So it is a failure of quantum field theory. It's a physics failure, not just a language.
Yes, but is it physics failure, or is it failure of does it mean that you don't understand reality, or does it mean that there is nothing to understand?
No, it means neither one. It means reality is not quantum field theory.
Okay.
So what I want to do with this is take that lesson. So the moral of the story, I mean, it's very, very important to make the statement clear, which hasn't been done yet by me or as far as I know by anybody. But the moral of it is supposed to be that you should only sensibly talk about quantum field theory within one horizon volume at a time, not add up many, many. And that's going to have obvious implications for the multiverse, which will have obvious implications for the cosmological arrow of time. One last question.
There was a very general, I mean, of course, this is being talked about at a sufficiently high level of hand-waving
Right.
that
I can read about anything.
maybe one doesn't know exactly what to say. But just on the level of sort of tone, a lot of what you were saying before had to do with pursuing a project of taking the applicability of quantum mechanics very seriously. And to the extent that that ran into geometrical problems, supposing that the geometrical problems on sufficiently close examination were going to go away, or that the very notion of geometry
It's not the right way to
go
go
away. Here you seem to be taking the opposite attitude on this, for reasons that I don't understand.
No, I don't think so. I mean, maybe I gave that impression wrongly. This is what exists. And what I take this discussion to indicate is that there are different ways that we might imagine representing this quantum state as the space of square rootable functions over some classical configuration space. In this case, where you have the horizon, it is not true that the quantum state can be represented as the space of square rootable complex functions over the configuration space of fields defined on this spatial hypersurface.
I see. This anticipates some other as yet undiscovered way to represent it? Or the thought is rather, no, what we're going to be stuck with is two different ways of representing it. One, one which goes from the outside and then goes around the surface of the black hole, and the other which starts from the inside.
Yeah, I see no obstacle in principle to developing a rigorous other way of representing the state. It would presumably be in the form of quantum field theory outside and then some non-local stuff on the stretched horizon of the black hole. But there might be a duality that says there's another way of talking about the same quantum state which makes it look like QFT inside. And likewise when we get to cosmology, which we'll do in 25 minutes. Thanks.